Welcome to this session. Today we are going to discuss lattice theory. In the last class, we discussed how to find out the extremal points of a partially ordered set. See how to find out the maximum values, minimal values, least values, greatest elements, what are the upper bounds and what are the lower bounds, what is the least upper bound, greatest lower bound, and so on. Now, a partially ordered set, whatever the partially ordered set, is said to be lattice, in that every pair of elements, if you are going to consider, it has a least upper bound and the greatest lower bound. In such case, that partially ordered set is known as a lattice. Lattice is a partially ordered set in which every pair of elements A, B belongs to L, which is having the least upper bound and the greatest lower bound. Then such partially ordered set is known as lattice. Now here we are going to consider some of the things. See, A join B, A or B. We are going to represent A join B, which is denoted as the least upper bound. This is known as the least upper bound. We are going to define with the symbol A or B. We are going to represent this as A join B. And the greatest lower bound of any two element subset, which is denoted as like this, then we are calling it as A meet B. A meet B. Instead of finding the least upper bound and the greatest lower bound, we are going to consider A or B, and A and B we are going to take in the places of least upper bound and the greatest lower bounds. Okay, we are going to discuss some of the partially ordered sets are given, and we have to verify whether the partially ordered sets are lattice or not. So let us consider the first one is, it is A is given like this. The set A is, it has given as, so 1, 3, 6, 9, 12. The set is consisting 5 elements. The set is consisting 5 elements. Of course, the divisibility relation will be there. So, whenever divisibility relation will be there, then 1 divides all the elements. So, I am going to take it as 1 at the bottom. So, 1 divides 1, 1 divides 2, 3, 1 divides 6, 1 divides 9, 1 divides 12. Next, I am going to consider the second element, 3. 3 divides 6 and 9 both. But 6 and 9 there is no relation between them. So they are incomparable elements. So we are taking it as in the next level. So whereas 3, there is a relation. 3 divides 6 and 3 divides 9. Of course, 3 is related to itself. And 3 is related to 12 also. 3 divides 12 also. Now, 6 divides 12. So, I am going to take, this is 12. This is 12. So, now, I have to consider like this. The partially Hasse diagram of the first one is like this. Now, from this Hasse diagram, we are going to verify whether it is a lattice or not. So, in this, we have to consider any pair of subset. So, that means a 2 element subset if we are going to consider. I am going to consider 1, 3 elements. 1, 3 belongs to A. Then 1, 3, what is the least upper bound? What is the least upper bound of 1, 3? So the least upper bound, as we discussed in the previous class. So what are the upper bounds? 3, 6, 9, 12. So the least upper bound is 3. And the greatest lower bound of 1 and 3 is 1. So if I am considering a subset 1, 3 of A, which is having least upper bound and the greatest lower bound. Like that, we have to select every pair of two elements. Every pair of two elements. Let us, I am going to consider 6, 9 is another subset, 2 element subset. So, which I am going to take belongs to A. Then, what about the upper bound, least upper bounds of 6, 9, 6, 9. So, 6, 9, the least upper bound is. So, the element which are related, 6 is related to that, 9 is related to that. So, there is no element because 6 is related to 6 and 9 is related to 9. 6, 9, there is no relation. And of course, there is no upper bounds for this. There is no upper bounds of this. So, there is no least upper bound. There is no least upper bound. So, the least upper bound is not there. So, whenever any subset of two elements set from the given set, if it is not having the least the least and the greatest lower bound, greatest lower bound or least upper bound, any one is not possible, and then it is not at all a lattice. Of course, I can consider what is the lower bound, greatest lower bounds of 6 and 9. So, of course, I am going to consider, I am going to get 3 is the greatest lower bound, but there is no least upper bound. But there is no least upper bound. So, we can say that the first one, the given Hasse diagram, is not a lattice. That means the first problem is not a lattice. Is not a lattice. Whereas the second one, if I am going to consider this, B, this is B. Whose Hasse diagram is this? This is A. Here in this, the set A is, the second one, the set A has 2, 4, 8, 16 is there. Now, 2 is related, 2 divides all the other elements. So, I am taking, it is related, so at the bottom. And of course, 4 is also related to 8 and 4 is also related to 16. So, I am going to write at the top. And of course, 8 is related to 8 itself and of course 16. So, next I am writing this and 6. Next I am going to take this. So, here, this is the Hasse diagram for the second one. This is nothing but a totally ordered set. So, any pair if you are going to consider, either A is related to B or B related to A. So, this is a totally ordered set, of course, and we have to verify whether it is a lattice or not. Consider any pair of elements of A. Any pair elements of A. That is, I am going to consider 2 and 16 belongs to A. Then what is the least upper bound of 16? So, which is nothing but the 16. And what is the greatest lower bound of 2, 16 is 2. Is 2. So, I am going to take another two elements, other two elements. Let us say 2, 4 belongs to A. What is the least upper bound of 2, 4? So, I am going to get 4. What is the greatest lower bound of 2, 4? I am going to get 2. I am going to get 2. So, like that, you can consider any pair subset of A from this, and we can get a least upper bound as well as the greatest lower bound. So, 4, 8 if I am going to consider belongs to A. So, here what is the least upper bound of 4, 8 is 8, and what is the greatest lower bound of 4, 8 is 4. So, in this, that's why we can say that any pair of elements of A, we can have greatest lower bound and least upper bound. So this partially ordered set, we are calling it as a lattice. We are calling it as a lattice. Let us consider the third one. Z is, okay, we are taking it as a Z is the integer set and the relation is greater than or equal to. Greater than or equals to relation. Now we have to verify whether this is a lattice or not. So for that, first of all, construct the Hasse diagram for that. So Z greater than or equals to G. So for this, Z is an integer set and the relation is greater than or equals to. So we are going to get, so this is an infinite set I am going to get. Infinite set I am going to get. Let us start with somewhere else. 2. Let us, I am just taking 2 is greater than 1. And of course 1 is greater than 0. And 0 is greater than minus 1. And of course minus 1 is greater than minus 2. And so on. It will be continued. It will be continued. Now you take any pair of elements. Any pair of elements. Suppose Z I am taking minus 1 comma 1. I am just taking a pair of elements in Z. So what I am going to get? The minus 1, 1. The least upper bound is 1 and the greatest lower bound I am going to consider minus 1, 1. The upper bounds are, that is nothing but, no, it's not like this. So it is the minus 1, 1, minus 1 greater than, the least upper bound of minus 1, 1, which is equals to, so the element which are related to both, so it is nothing but, this is 1 is greater than this, so 0 is greater than this, okay, so 2 is greater than this, and next this is also greater than, so I can take it as, okay, I can consider it as greater than or equals to, is a relation will be there, so I am just taking 1. And of course, the greatest lower bound, if I am going to consider, I am going to consider it as minus 1. So every pair of elements, if I am considering from this side, so the least and the greatest elements are exist for this. So this is known as a lattice. Of course, the set is consisting infinite elements. So we can say that it is a infinite lattice. Infinite lattice. I am just taking 0, 1, let us say, belongs to Z. So what I am saying that 1 is greater than or equal to 0. So 1 is related to 0. Next another one is, of course, 0 is related to 0. So what is the element? The element is nothing but what is the Z is consisting. And so on, minus 2, minus 1, 0, 1, 2 and so on. This will be there. Now you observe this. 1 is greater than this one. Of course, 1 is greater than or equals to this one. So the least upper bound is 1. Least upper bound is 1. And the greatest lower bound is nothing but 0 is greater than minus 1. So 0 is greater than minus 1. So I am saying that greatest lower bound is 0. Greatest lower bound is 0. So in any order, if you consider a pair of two elements, a pair of subset of Z, so which is having least and the greatest values. So, least upper bound and the greatest lower bound, then we can say that partially ordered set is known as a lattice. So, this we are saying it as this Hasse diagram or this set is itself is known as a lattice. Now, the other concept is, so D is, so what is it? Is a power set of A, and the relation is nothing but it's a subset, and this is a superset. This is subset, and whereas this is a superset. Okay, so now I am going to discuss. This is this. So what is let us consider the relation represents this. A is a superset of B. A is superset of B. So now what is a power set is consisting? Power set is consisting is nothing but set of all subsets of A comma B, because A is mentioned as A comma B. So the powers, of course, two power A comma B comma C. Of course, it is 3 elements will be there. There are 2 power 3, that is 8 elements will be there in the power set. 1, 2, 3, 4, 5, 6, 7, 8. So all possible subsets are this one. Now we have to verify. We have to first of all construct the Hasse diagram for this. So here, let us, I'm just considering. So this is one set. Let us, I'm just taking A, B, C. So the next level, there is no comparison between these two. So we are going to get another one is, so I'm just taking A, B, and the next another one is AC, and another one is BC. Next another one is BC. So this is, so observe this, this is AC. So now AC, let us AC is a subset of this. Of course, ABC is a superset of AC, and next this is a superset of this, and this is the superset of this. Now, of course, AB, then this is, I'm going to write A, I'm going to take A, and I'm going to write it as B, and I'm going to take it as C. I'm going to take it as C. Somewhere else, A, and I'm just taking I'm just considering, let us say B, and I'm going to take it as C. Now BC is a superset of, let us take this, and now A is, I'm just taking, this is A, let us say A is a superset of this, and of course AC is then AC, of course A is this and C is this. Okay, next B. BC is a superset, B is a subset, of course I'm taking B is a subset, and of course C is a subset, and now AB is a superset of B, and of course the last one is, let us taking it as the null set. So this is what we have, null set, and ABCs will be there, and V. So these are 5. B is a superset of null set, this is, and this is. So this is the Hasse diagram for this. So Hasse diagram for D, which is a power set of A, and of course a superset. Of course a superset. So now if you are going to completely reverse this, if you are going to reverse this, then we are going to get the next one. So what is this? This is the, we are going to get. So is a subset. Just we are going to consider the elements in the opposite. 5 comes to here, ABC will go to there, and we are going to get the subset relation. Subset relation. Now you observe here, you consider any 2 element set, any 2 element set, whatever the way that you are going to consider. Let us say I am just taking, this is the 2 element set, B, AB. So which is having the least upper bound is B and the greatest lower bound is AB. So like that, any pair if you are going to consider, I am just taking these 2. I am just taking these 2, ABC, BC. So what is the greatest lower bound is BC, least upper bound is BC, and greatest lower bound is ABC, like that. So any pair if you are going to consider, so if I am taking like this, so the upper bound, least upper bound is 5 and the greatest lower bound is B. So like that we can get all the for every pair of elements it has the least upper bound and the greatest lower bound. So we can say that this Hasse diagram is known as a lattice, And of course the next concept is this is a reverse. We are taking power set of A, which is a subset will be given. So just we are going to reverse this diagram. Then we are going to get that Hasse diagram. Of course, it is also a lattice. So observe this. What are the least elements are? Least element and the greatest element are this top and bottom. Okay. So minimal and maximal elements are also same. And whenever the least and the greatest elements are exist, for such cases, the elements are itself is known as a maximal or minimal elements. So while we are considering either this one or this one is or this one, this is only it's not a lattice, and the remaining all are lattices, Okay. Now, what is a sublattice? Let L, R be a lattice and M be a subset of L. Then M is called a sublattice of L. If the least upper bound we are selecting from A, any two elements we are selecting from M, that means we are considering whatever the pair of elements. Earlier we said that the pair of elements are selecting from the set itself. Now we are going to select the pair of elements from the subset. And every pair of elements will have the least and the greatest elements are exist. Then we can say that subset is known as a sublattice. That means it's nothing but a subset which satisfies all the lattice conditions, which is known as a sublattice. So here it is given. Let us one example: divisors of 30. And here divisors of 6 and divisors of 10 and divisors of 15, because 6 divides 30 and 10 divides 30, 15 divides 30. So obviously we can get these are the subsets. So we can show that these subsets are lattices, because it is a subset of this, so we can say it is a sublattice. So what are the D30? D30 is just we have to consider the elements from 1 to 30. 1 is divides 30, 2 divides 30, and next 3 divides 30, and next 4 is not divides, next 5 divides, next 6 divides, next 7 is not, 8 is not, 9 is not, 10 is divides, 11, 12, 13, 14, 15 divides, then 16, 20, 25, next except 30. So divisors of 30 is consisting 1, 2, 3, 4, 5, 6, 7, 8 elements. So the set of all elements up to 30 who are divides 30, those elements we have to consider. Now you can consider D6. D6 is 1, 2, 3, 6. Obviously it is a subset. D10 if you are considering 1, 2, 5 and 10 is also a subset. 1, 3, 5, 15 is also a subset of this. So these are the subsets of D30. So now we have to verify whether D30 is a lattice, and of course we are going to show that the subsets, that is D16, D10, D15 are subsets. Now let us consider, this is the diagram of the D30. So it is D30 No, it is a D60. This is, let us, we are going to change this. I'm just taking, let us, I'm just considering 60. D60. Let us, the divisors I'm just taking. So, now, so the divisors of, let us say, 15 and the next 16, 17, 18, 19, 20 will be there. Then I'm not considering 60 and I'm just taking 60 divisors. 60 divisors. So it is 30 and of course the next one is 60. So we have to add two more. So it is then it is a 10, then it is a 15, then it is 20, then it is 30, then it is 60. So it is a divisors of 60. So now let us go for this. This is not divisors of 30, the divisors of 60. So now we have to take this. So 1 and 60, 1 is related to all the elements. So here 2, 3, 5. So there is no relation between these three elements. So we are taking at the second level. And at the third level you observe 4, 6, 10, 15. There is no relation between them. And 12, 30, 20, 30. There is no relation. And of course the 60. So here you observe this. You draw this. This is 1 is divides 3 automatically. So it will be 20 divides 60, 30 divides 60, 10 divides 30. Like that it will be there. Like that it will be there. So these are the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 elements 1, 3, 4, 4, 4, 8, 9, 10, of course 11. Left means what is the other element is 6 is also will be there. 12 is there. 12 is another element. 12 5 is 16. So it is then it is 10 and 12. So 11, 12 elements will be there. So those things we are going to representing in this, and here it will be, then automatically we can say that it is a lattice because you can consider any pair of elements. So let us say 10, 20 belongs to D60, Then 10, the least upper bound of 10, 20, least upper bound is 20. Then the greatest lower bound of 10, 20, it is 10. It is 10. Like that you can consider anything. 1, 60 belongs to D60, divisors of 60. So 1 least upper bound is of 160 is 60, and the greatest lower bound of 1, 60 is 1. So like that you take any pair 20, 12 and 30 if you consider in D60, then 12, the 30, 12, 30. So which is nothing but 60, and 12, the greatest lower bound of 12, 30, the greatest lower bound is, here I am getting, this is 6, this is a 6, okay, like that. So for every pair if I am going to consider, it has a least upper bound and the greatest lower bound. So we can say that it is a lattice. It is a lattice. Now let us consider the D6 divisors of 6. So 1, 2, 3, 6. 1, 2, 3, 6. Where it is 1, 2, 1. This is, you observe this 1, 2, 3, 6. So whenever 1, 2, 3, 6, if you are going to consider 1, 2, 3, 6. So here any pair if I am taking 1, 6, if I am taking 1, 6, the least greatest lower bound is 1 and the least upper bound is 6. And if I am considering 2, 3, if I am taking 2, 3, the least upper bound 2, 3 if I am considering. So 2, 3 least upper bound is 6 and the greatest lower bound is 2, 3 is 1. 2, 3 is 1. So like that. So whatever the elements if I am considering. So it is 2, 6. Let us consider 2, 6. So T6 from D6. Then the least upper bound of 2, 6 is 6 and the greatest lower bound of 2, 6 is 2. So we can say that it is a lattice. So it is a subset of this. So we can say that it is a subset of sublattice. Similarly, 1, 2, 5, 10. So 1, 2 and whatever is 5, 10. So if I am taking 1, 2, 5, 10, 1, 2, then this is 1, 2, 5, 10. So obviously this is also, you observe this 1, 2, 5, 10. So here also any pair 2, 5 if I am taking, the greatest lower bound is 1 and the least upper bound is 10. So like that, if I am taking 2, 10, then obviously least upper bound is 10 and the greatest lower bound is 2. So like that, we can say that D10 is also a sublattice. So like this, we can say that whatever the subset you are considering from the given set and which satisfies the lattice properties, then we can say that is also a sublattice. Now, bounded lattice. There are different types of lattices will be there. So in that first, let us consider the bounded lattice. So bounded lattice, a lattice when we say that it is a bounded. So a lattice, L is said to be bounded. It has the greatest element and the least element. The greatest and the least elements are represented with 1 and 0. Greatest element is 1 and the least element is 0. So any lattice, right, almost all the lattices are bounded lattices only, because every lattice, if you are going to consider, it has a least and the greatest elements will be there. So such lattice is known as a bounded lattice. So here the least element we are calling it as 0 and the greatest element we are taking it as 1. So whenever anything is AB, any element will be there, then we can call it as that lattice is a bounded lattice. Okay. Then some identities will be there. So if I am taking the least upper bound of 0 or A0 will be the same. That is nothing but in a set, it's nothing but a 2 element set. In any set, that means either it satisfies a commutative law. That means either 0 or A or 0. If I am taking, so for anything, the least upper bound is A only, and similarly the greatest lower bound in any order we can take, it should be 0. And next, so these are some of the identities that we are going to conduct. And now, what is another type of lattice is complemented lattice. A lattice is said to be a complemented. First of all, it should be a bounded lattice. Okay, and it has a bounded lattice when it has a greatest and the least element will be exist. And any 2 elements if I am going to consider, so the least greatest lower bound should be 0, that is the least element, and the least upper bound should be equal to 1. Such bounded lattice is called as a complemented lattice. That means if we are going to consider any pair of elements, the greatest lower bound is nothing but the least element. The least upper bound is nothing but the greatest element. Let us consider one example. I am just taking A, B, C, D. Let us, the set is A is equals to A, B, C, D, whose RC diagram is given like this. Then what is the least element is? Least element is A, and the greatest element is D. Greatest element is D. Now consider, this is a bounded lattice because it has least and the greatest elements. So it is nothing but a bounded lattice. Now a bounded lattice is said to be complemented lattice if any pair, if I am considering. So let us say B comma C I am taking. B comma C belongs to A. Now what is B comma C? The least upper bound of B comma C. BC upper bound is D only. Only one upper bound, automatically the least upper bound is the greatest value. Is the greatest element. This is the greatest element. Greatest element. And next the greatest lower bounds. Greatest lower bound is only 1. The greatest lower bound is also 1. So then we can say that the which is equals to the least element. Which is equals to the least element. So for this lattice, which having least upper bound is equals to the greatest value, and greatest lower bound is the least element. So we can say that this lattice is a complemented lattice. Now let us consider another example. Verify the given lattice is a bounded lattice and it is a complemented lattice. Suppose let us I am just considering a Hasse diagram of one lattices. Let us say I am taking the lattice. I am just taking D, E, F and G, H, I. Let us say. So here the greatest element is A, and the next the least element is A, and the greatest element is I. So this lattice is having least and the greatest elements. So we can say that it is a bounded lattice. Now we can say that whether this bounded lattice is a complemented lattice or not. In any complemented lattice, for each and every element, see here earlier whatever we are saying that, see here B and C, B or C is equals to D. That means the least upper bound of B comma C is D. Then we can say that B and C, the least element, then we can say that B and C are complements of each other. The elements B and C are complements of each other. So in any complemented lattice, we can take any element. Definitely it has at least one complemented element. Otherwise, it does not have a complemented lattice. In another way we are saying. See here, the least upper bound and the greatest lower bound, if it is equals to the least and the greatest elements, then we can say that both elements are complemented of each other. Suppose if I am taking A and D, so A and D, what is the least upper bound is D, which is nothing but the greatest element, and A and D, that is nothing but the least greatest lower bound is A, so it is nothing but the least element. So I can say that A and D both are complements of each other. A complement is D, D complement is A. Similarly, B complement is C, or C complement is B, C complement is B. So in the set A, B, C, D, every element will have at least one complement. So we can also say that the given bounded lattice is a complemented lattice. Or another way also we can say like this also. Both are same. Now let us go for this. So I am just considering this. The lattices. It is having least and the greatest. Least and the greatest. So it is a bounded lattice. It is a lattice is bounded. Now we have to verify. We have to verify any two element set. Let us take D, E. D, E. D, E. What is it? I am taking D, E from, let us say, the set A equals to A to, let us say I am taking I. A, B, C, D, E, F, G, H, I. A to I. Okay. So let us A. Then what is the least upper bound of D, E? D, E least upper bound G, which is not the greatest element. Which is not the greatest element. And D and E, the greatest lower bound. DE lower bound is B, which is not equals to the least element. Which is not equals to that least element. So D will not have, or I'm saying that E will not have a complement. Or I can say that it is not a complemented lattice. Or else if I am taking, suppose another element, let us say DF belongs to A. Then what I am going to take? DF. What is the least upper bound of DF? Least upper bound of DF is, so DF is least upper bound is I, which is nothing but the greatest element. And next, what is the greatest lower bound of DF? Of course it is A. Of course it is A. So which is the least element? So I can say that D is having a complement F. D is having a complement. What is that complement is F? And of course F is having a complement of complement is D. And what about E? E is E. I'm saying DE. So E is not the complement of D is not the complement of E. And similarly, I'm taking EF. EF. What is EF? The least upper bound is H, which is not equals to the greatest lower bound. So I can say that E and F, let us say, E will not have a complement. E will not have a complement. So I can say that this is not a complemented lattice. This is not a complemented lattice. It's not necessary by knowing the complement of each and every element. This is just in another way we are saying. So whenever any complemented lattice, if you are considering the previous one, so each and every element will have a complement. And here it is only a bounded lattice, and each and every element will not have a complement. So I can say that it is not a complemented lattice. It is not a complemented lattice. Or else I am just taking like this also. I can say that it is not a complemented lattice. It is not a complemented lattice. Okay. In another way also I am just considering DE or F, GH if I am taking. GH belongs to A. So what I am going to get? What are the lower bounds? So what are the upper bounds is GH. I am just taking I. I is the greatest element. And what about the greatest lower bound is, I am just taking E, which is not equal to least element. Which is not equals to the least element. So from this only you can say that it is not a complemented lattice. Complemented lattice. Let us go for the other one. So if I am taking another example, let us say this is A and I am just taking this is B. Now, and let us, I am just taking A, B, C, D, E, F, G. So it is having least element and it is having greatest element. So we can say that it is a bounded lattice. It is a bounded lattice. Bounded lattice. But if I am just taking it is a bounded lattice, but it is not a complemented lattice because I am just taking, let us take any element. Let us say I am finding about for C and D, CD. So here what is, I am saying that of course BD if I am considering, what is the least upper bound? Is equals to C. Least upper bound is equals to C, which is not equals to the greatest element, So I can say that it is not a lattice. By inspecting only I can say that. So here BD, if I am taking BD, then what I am going to get? A is the greatest lower bound, no problem. And what is the least upper bound is, of course it is Z. And now, so here it is E if I am considering, if I am taking, let us say BE if I am taking this one. What is the least upper bound? Least upper bound is E, and which is not the greatest element. And what is the greatest lower bound? B. So BE, if I am taking BE, what is the least upper bound is E. And what is the greatest lower bound? BE is B, which is not equals to greatest element, which is not equals to least element. Greatest element and which is not equals to least element. So, which is not a complemented lattice. So here, once again, I am just taking what is a lattice and the lattice, and next when we say that a partially ordered set is said to be lattice, and what are the different types of lattices? In that, one is bounded lattice and another one is complemented lattice. Complemented lattice in any way, just general, I am just taking, suppose a bounded lattice which is having least element and greatest element, then any two elements if I am going to consider, then an element B is called a complement of A. So here simply they are saying it is a complement of A. B, when B is said to be a complement of A, So whenever the least and the greatest elements are equals to minimum and maximum values, then we say that they are complements of each other. So here also BC, B complement is C, C complement is B. And here also A, B, A, D. So we can say that A complement is D, D complement is A. So for each and every element, there are complements are exist. So we can say that it is a complemented lattice. The other graphs, there is no complements are not exist. So if I am taking E does not have any complement. But D is having a complement, F. And of course, F is having a complement, D. And of course, if I am considering these two, so here I cannot say that what about G, and G will not have any complement. Let us say DG. So DG, the least upper bound is G, and the greatest lower bound is D, which is not the least and the greatest element. So they are not the complements of each other. So E, G, and at least one element, if it does not have a complement, then the entire lattice is not a complemented lattice. So here E does not have a complement, so I can say that it is not a complemented lattice. So similarly, here also I am considering E and F. Suppose B, E, or else I'm just taking C. If I'm taking C, what about BD? If I'm taking E, let us say, if I'm taking E, so what about BD? This is E. So B is not complement, whereas these two, I can say that least upper bound of FD and EF if I am considering, so the greatest lower bound of EF I am going to get the least element, and the least upper bound of EF I am going to get the, so the complemented lattice is nothing but in every element in the set which is having a complement, then we can say that it is a complemented lattice. Otherwise, it is not a complemented lattice. So when we say that two elements are complemented of each other, the least and the greatest lower bound equal to the least element, and the least upper bound is equals to the greatest element, then we can say that those two elements are complements of each other. So whenever A and B equal to least element, A or B equals to greatest element, then A is a complement of B or B is a complement of A. So whenever this thing is exist for all the elements of L, then it is a complemented lattice. So in this example, so L is having A, B, C, D. All elements will have a complements. A is having a complement D. D is having a complement A. C is having a complement B. B is having a complement C. So automatically it is a complemented lattice. And whereas here, so if I am considering DE, the least upper bound is G, which is not at the greatest value, and DE, the greatest lower bound is B, which is not the least one, and so EF, if you are considering the greatest value, the lowest greatest lower bound is not the least, and the least upper bound is not the least. So we can say that E does not have any complement, whereas D is having complement which is equal to F, and F is also having complement which is D, but E does not have any complement. In the similar sense, we can consider BC. So BC, the greatest lower bound is of course A, which is the least value, and the least upper bound which is equal to E. So we can say that BC are not complemented of each other. So our B does not have a complement. B does not have a complement, or C does not have a complement. So it is not a complemented lattice. In the same sense, the next one is also not a complemented lattice. It is not a complemented lattice because E is not a complement, because E is not a complement. So we can say that it is also not complemented lattice. So tomorrow in the next session we are going to discuss some more different types of lattices. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.